In this video, I'm going to show you a surprising use of continued fractions. When you have a quadratic equation, like x squared minus 4x minus 3 equals 0, since it doesn't factor, you might feel like you have to use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a, which is 4 plus or minus the square root of 28 over 2, which is 4 plus or minus 2 root 7 over 2, which is 4 plus or minus 4 plus or minus regular root 7. And I'm interested in the positive answer now, which is, it's not 4, it's 2 plus. I'm interested in the positive answer, which is about 4.65. And this is the standard way to do this. It doesn't factor. You could use completing the square as another option. But here's a third option that seems like it would lead to a dead end. And here's what it is. What if, and I'm going to use this mainly if I have a negative sign here and here, what if instead I added the 4x and the 3 to both sides? Well, this is definitely considered to be bad form on the algebra regions, but let's just see what happens. And what if now I divided both sides by x? I get x equals 4x over x is 4. Okay. And we look at this equation and say, well, that's really not that useful. If you gave me this x equals 4 plus 3 over x equation, the first thing you would do is multiply both sides through by x to turn it back into this, and then you'd move everything over to one side so you can use the quadratic formula. But what if I did something a little different here? What if I took this x equals 4 plus 3 over x, and you see this x here, what if I would replace that x with, or maybe I should say with this, because you see you have an x here also. So if x is 4 plus 3 over x, that's true for this x in the denominator also. So it would turn into 4 plus 3 over, but instead of writing x, I'm going to write this entire 4 plus 3 over x. Well, that has an x in the denominator also, so I could replace that x with 4 plus 3 over x. And I could keep doing that, and I would end up with this funny continued fraction expression. And now I'm just going to say dot, 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 like that. So what this is an infinite continued fraction. And it's not a simple continued fraction because the numerators are not ones. So this is an infinite continued fraction. An infinite continued fraction could have ones in the numerators and be a simple infinite continued fraction, but in this case, so you might think, well, that's kind of neat looking, but how is that useful? Well, when you have an infinite continued fraction, 4 plus 3 over 4 plus 3 over 4 plus 3 over dot, dot, dot. We can approximate it by taking what are called the convergents. What's meant by convergence is, what if I erased everything after the first plus sign? Well, that wouldn't be exactly what this expression equals, but it would be fairly close because it's 4 plus some fraction. So 4 is our first convergent. Our second convergent is, what if instead of erasing everything after the first plus sign, I erased everything after the second plus sign? I would end up with 19 over 4. Which is 4.75. Now I'll show you a little trick for the next conversion. So the next expression will be 4 plus 3 over 4 plus 3 over 4. Now to calculate this out, we actually don't need to start over from scratch, because see the last one, the 4 plus 3 over 4? That's actually in the denominator here. And that's always going to happen. So I could write this as 4 plus 3 over the most recent answer, which turns into 4 plus 12 over 19, which turns to 88 over 19, which is about 4.6. And for the next one, the same kind of thing is going to happen. This entire expression ends up being in the denominator of the next one. So I get 4 plus 3 over the previous answer, which was 88 over 19. Let's go over here. That turns eventually into 409 over 88, which is about 4.65, which is a good approximation for 2 plus root 7. It gets us the positive answer. So with no square root or no square root algorithm or anything, I'm able to get a nice approximation for the answer to this quadratic equation, x squared minus 4x minus 3 equals 0. Something else to just kind of notice: the first conversion is less than the actual answer. The second conversion is greater than the actual answer. The third conversion is less than the actual answer. And the fourth conversion is greater than. So it alternates between greater than and less than. Okay, now would you take some time to work out the first 4 convergents to the equation x squared minus 6x minus 2 equals 0? You'll know that it's working out if your answer, because that the actual answer is 3 plus radical 11 if you were to do the quadratic formula, which is a little bit bigger than I think it's about 6.31. So would you go through this process and work out the first 4 conversions, put them as improper fractions, and then if you want to change them into decimals to make sure you're on the right track, if the answers are getting closer to 6.31, and then you can just put all the answers as improper fractions. You can go ahead and do that now. Okay, you should end up with, here's our process, 6x plus 2, which means x equals 6 plus 2 over x. The first conversion is 6. The second one is 6 plus 2 over 6, which is 6 1/3, which is 19 over 3. The third one is 6 plus 2 over 19 over 3, which turns into 120 over 19. And the fourth one is 6 plus 2 over 120 over 19, which ends up being 756 over 120, which is about 6.3. It's probably useful to expand this thing, just to kind of, if you have trouble seeing why that's true. So let me show you sort of the longer way. X equals 6 plus 2 over 6 plus x. Hold on, let me go back to this. Plus 2 over x. And then replace the x with 6 plus 2 over x. And then replace that x with 6 plus 2 over x, and just make the dot, dot, dot. That might help you see it a little bit better. But what is going to end up happening always is that each answer ends up becoming the denominator of the next one. So you do 2 over that, and then add 6, and you will end up with the next convergent. Okay, the other skill I want to show you is how you can take this process and reverse it. So here's an infinite continued fraction with a repeating pattern to it. And, well, we can't, it's hard for us to do all the conversions for this, but we actually could, even though it goes on forever, we could work out 4 would be the first convergent, and the next one would end up being 4 plus 5 over 4, and it would go on. But actually, I'm not going to do that at all. Instead, I'm going to do something very sneaky. So x is 4 plus 5 over 4 plus 5 over 4 plus 5, all that. Check this out. In the denominator of this fraction, 5 over, that expression in the denominator, 4 plus 5 over 4 plus 5 over going on forever, is actually the same, because it's infinite, as the original expression itself, 4 plus 5 over 4 plus 5 over 4 plus 5. This reminds me a little bit of when you see a picture of like a person who's holding a picture of themselves, and that little person is holding a picture, and so on and so on. So when you see an expression like this, check out what you can do. You can replace this entire denominator, 4 plus 5 over 4 plus 5, and so on, with just an x. And now we can multiply both sides through by x. And we can solve this quadratic equation. And in this case, it factors. And we get x equals 5 or x equals negative 1. Now we're just going to keep the positive answer because, of course, this is already 4, and 4 plus something is not going to get to negative 1. So x equals 5 is the answer. Would you do the same thing for this? Remember, if it doesn't factor, you have to use the quadratic formula. Okay, so take a minute to work out the answer. What is the exact value of this infinite continued fraction? Take a minute to do that. Okay, we can see here this denominator is equivalent to the entire x expression. Seems weird because it seems like it has a couple of fewer numbers in it because one is a subset of the other, but with infinities, it doesn't work that way. X squared equals 8x plus 3. X squared minus 8x minus 3 equals 0. It doesn't factor, so we got to use the quadratic formula. 8 plus, I'll just do the plus because it's not going to be the negative answer. 64 plus 9 over 2, and we end up with 8 plus radical 73 over 2. That's the answer to this question. That's the exact answer to this infinite continued fraction. So what we're seeing here is that infinite continued fractions can be a way of representing irrational numbers with a sort of pattern, a nice looking pattern at least in the denominators and the numbers that are in the continued fraction. Okay, that's it for today.